If a language model relies on a static list of whole words, it cannot process anything outside that specific list. It effectively becomes blind to any word it hasn't encountered in its training data. To solve this, the model uses tokens, smaller subword units. By splitting a fabricated word like unfrickin' believable into recognizable chunks, un, frickin', and believable, the model can identify the meaning of the components even if the whole word is new. By processing these subword units, the AI represents rare strings as combinations of known pieces. This allows the system to map vast text back to a manageable, predefined set of tokens. The standard method for generating these tokens is an algorithm called Byte pair encoding. The rule is strictly mechanical. Break a dataset into individual characters, find the most frequent adjacent pair, and merge them into a single unit. We isolate the math using an abstract toy corpus of 10 single characters. We scan the text to find the most frequent adjacent pair. A followed by B appears 3 times. We merge them into a single block, shrinking the corpus length. This frequency-based statistical rule is how language models construct their vocabulary from a training set. Let's apply this to real English words. On the left is our training corpus, containing counts of 4 simple words. And on the right is our starting vocabulary of individual characters. We count the adjacent pairs across the corpus. The pair N followed by E appears 4 total times in new and renew, making it our most frequent pair. To process this correctly, the algorithm must follow a dual update rule. A merge alters both the permanent dictionary and active text. Step 1. We add the merged token NE to the right side vocabulary. Step 2, we return to the text, replacing every instance of N and E with our new single token. Failing to perform both updates desynchronizes the model's memory from its processing. If the text isn't updated, the system will continue to count old characters that should no longer exist, stalling the algorithm. Look at the updated corpus. What is the next BPE merge? The token NE and the letter W appear together 4 times. We run the dual update again, snapping them together in the corpus to form new and adding it to the vocabulary list. This shows how the process works in practice. A machine with no prior knowledge of English syllables or definitions can construct a valid word purely by counting adjacencies. In real large language models, this process is repeated k times, where k is a set hyperparameter, usually reaching into the tens of thousands. Scaling this process allows the model to naturally discover linguistic affixes. Over thousands of passes, the algorithm learns that R and E merge into RE, which frequently attaches to new to form renew. This creates a critical failsafe when the model encounters a word it hasn't seen before, such as a new. Rather than failing, the model falls back on its learned vocabulary of pieces. It segments the word into the base character A and the learned token new. By building from individual characters up to words and prefixes, BPE provides the model with the necessary components to process any text it encounters. Split to characters, count frequent pairs, and always update both the text and the vocabulary.